Welcome back. That was probably the calmest section of the Bach chaconne. It's easier in some ways, there aren't that many notes, but it's much harder in other ways. If you play it a little out of tune, some of those notes I played were just a little out of tune, and when you play some of those notes out of tune, people notice. That's because you hear dissonance, and that's what today's lecture is about, dissonance, that sort of rough, slightly unpleasant sound, especially when things are a little out of tune. First, let's review. We now understand a single note and its vibrations, and we understand a sequence of notes called a scale. Today we're going to talk about two or more notes played at the same time, a chord, like some of the chords you just heard in the chaconne. Now, not all combinations of notes sound good, and today we're going to talk about the mathematics of dissonance when they don't sound so good, and the musical implications of that. Let's look a little closer at this opening music. You see, not all intervals are created equal. Musicians work really hard to get some intervals perfect and don't have to work so hard, don't have to care so much about others. Let's hear a particular line in the opening music. So there's 4 chords in there. That first interval is a minor third. It's not that important to get that exactly in tune. And then we have a major 6th and a major 7th. Also not that important, and then we hit the octave. When I miss it a little bit, oh, it sounds horrible. It's very important to get your octaves exactly in tune. Violinists practice octaves for hours to get them exactly in tune. If I miss some of the other intervals, the minor third, the major 7th, you're not going to notice. But if I miss the octave a little bit, you're going to hear the dissonance. That's what we're going to talk about today. So what is dissonance? Dissonance is a discordant sound. It's produced by 2 or more notes sounding displeasing or rough. It's a sort of tonal tension. It's the opposite of consonance. Sometimes it's intentional. Sometimes composers will build dissonance for a tense moment and then release it by finding consonance. Today we're going to talk mostly about the dissonance of being out of tune. Now, as we know from the last lecture, being out of tune is sort of a complicated idea, but whatever your scale is, there is a sense of out of tune. Now, dissonance has a physical component that we're going to talk about mostly, but it also has a cultural component. I want to talk really quickly about the cultural component. What Bach considered beautiful, medieval composers might have called dissonant. Here's a chord from earlier in the chaconne. Medieval composers might have thought of that as incredibly dissonant, but Bach wrote it into the piece. What Stravinsky wrote when we fast forward to 1913, when he wrote The Rite of Spring, he asked the violins to play this chord. Now that might have been considered very dissonant by Bach, but Stravinsky wrote it into his piece. What's considered dissonant changes over time. Now mathematically, the Pythagoreans thought that consonants, nice-sounding notes together, had a ratio of frequencies with small numbers, and dissonance was anything but that. Hermann von Helmholtz, a German mathematician and physicist, gave a mathematical description of dissonance. For him, it involved the overtones as well as the fundamental notes, and we'll see that a little bit later. His explanation was that dissonance was beats. Now, beats are a phenomenon produced by 2 frequencies being played when the 2 frequencies are very close to each other. I want to clarify here because beat is a word with many different meanings. Now, I don't want you to confuse the term I'm using with things like what you do on drums or keeping time or what a conductor does, beating out rhythm, beating out the time signature. The Grove Dictionary of Music calls this kind of beats an acoustical phenomenon useful in tuning instruments resulting from the interference of 2 sound waves of slightly different frequencies. What we mean by that is it's a throbbing sound produced when 2 notes are played slightly out of tune with each other. And it's useful in tuning instruments. So, let's hear what beats sound like. Now, we heard them last time. We heard them electronically. We were playing sine waves. I want you to hear beats on an actual instrument. And so I'm going to play 2 Ds. I'm going to play one on my open D string here. And I'm also going to play another one on my G string here. And if I play them a little bit out of tune, you should hear beats. It's a throbbing sound. And one of the things I can do is I can change how frequently that throbbing sound is going by getting the notes closer and closer to each other. And what you'll notice is as the notes get closer, the beats slow down. If the notes get further apart, the beats speed up. And finally, if the notes are exactly the same, you get no beats at all. You just hear one note. You'll also note that if I play the notes very far apart, you don't hear beats at all. You just hear two separate notes. That's sort of clearly the and the other note. Today, we're going to understand the mathematics of dissonance and these beats, and we're going to look at the implications of these for musical performance and for piano tuning. There's a really important equation that we're going to refer to again and again today, and we're going to call that the beat equation. Now, this is actually just a trigonometric identity that you might have seen in a trigonometry class back in high school. But it's this, that the sine of A plus the sine of B is equal to 2 times the sine of the average times the cosine of half the difference. Now, when two notes are played at the same time, that's the left side of the equation, sine A plus sine B. And the cool thing is that sometimes when two notes are played at the same time, you hear the left side, you hear those two notes. But actually sometimes you hear the right side of this equation. And so your mind is going back and forth depending on which notes you're hearing. You're sometimes hearing the left side and sometimes hearing the right. Let's look at an example to make sure we understand this equation. Let's let A be 5t and let's let B be 3t. So now this equation looks like the sine of 5t plus the sine of 3t equals 2 times the sine of the average, which is 4t, times the cosine of half the difference. The difference is 2t, and half of that is just t. Now, for the math lovers out there, we're going to actually go through a proof of this later. It's not too hard to get a proof of this, but for now, we're going to just take that this beat equation is actually true. But let's look and see if we can see this in another representation. You remember that mathematicians love to look at different representations. So now let's look at and see if we can see this equation graphically with this example of 5t and 3t. We can graph the sine of 5t and it looks like this. And now we can graph the sine of 3t and we can look at what happens when we add those. When we're doing addition, the left side of the equation, we're actually doing pointwise addition. We find we pick some x value and look how high the sine of 5t is, and at that same x value, we look how high the sine of 3t is. We add those two heights, and that's what we get for the value of the sine of 5t plus the sine of 3t. And so that's how we get the left side of this equation graphically. Now let's look at the right side of the equation. The sine of 4t has a graph that looks like this. The cosine of t has a graph that looks like this. And now when we multiply, we're actually doing point-by-point multiplication. So now at a particular value of x, we're looking for the height of the sine of 4t and the height of the cosine of t, and we're looking to multiply those. And that's going to give us the sine of 4t times the cosine of t. Now you should notice that if either one of these functions is 0, then when we multiply them, we're going to get 0 for the product. The last thing we have to do on the right side of this equation is multiply by 2 to get 2 times the sine of 4t times the cosine of t. And that's what this function is here. Now let's compare that. We can compare that to what we got on the left side of the equation. That looked like this. And here's what we got on the right side of the equation. That looked like this. They look exactly the same. Let's zoom out just to see if we're being fooled by the scale of this. And when we zoom out, we see that even when we zoom out, those two graphs are exactly the same. We're confirming that it is an equation, that the left side really does equal the right side. So that was a graphical representation. Let's see if we can take this to a musical example. And in order to do that, let's change A and B a little bit. Let's take A to be 450 times 2 pi times t, and B to be 440 times 2 pi times t. These represent a 450 hertz sine wave and a 440 hertz sine wave. If you're wondering, the 2 pi comes because the natural period of sine and cosine is 2 pi. Now the sine of 450t 2 pi plus the sine of 440t 2 pi should be equal to, according to the beat equation, 2 times the sine of the average, and that's going to be 445t times 2 pi, times the cosine of half the difference. The difference is 10 times t times 2 pi, and half of that is 5 times t times 2 pi. Now let's look both graphically and musically at this. First, let's look at the sine of 440 times t times 2 pi. When we listen to that, here's what it sounds like. And you can see the graph of that. And if we look at the graph and listen to 450 hertz note, that's the sine of 450 t times 2 pi, here's what that sounds like. Now, of course, the notes that we just played, those were pure sine waves. If you were to hear it on a violin, you would hear a 440A and its overtones. And that's going to become important later. For now, let's see if we can add these functions and see what the sound sounds like when we add these functions. So here's a 440 hertz A, and this is what it looks like. And here's the 450 hertz A, and you can notice that it's slightly sharp. When we add them, we again do this point-by-point addition. And so we're adding at any particular x the value of the 440 hertz plus the value of the 450 hertz, and we get this function right here. And when we listen to it, you can hear the dissonance. Those are the beats that we're hearing. But when we look at it, it looks like just another sine wave. It looks maybe just 2 times as tall, but it looks like just a sine wave. But let's zoom out. And it's when we zoom out that we all of a sudden start to see what we were hearing before. You can see the beats now in the waveform. Those are the throbbing, waving, those are the acoustic phenomenon that we're talking about. That's the dissonance. So let's find out how the math explains what it is that we're hearing. In order to see that, let's look at the right side. Now the right side of the equation has the sine of 445 t times 2 pi, and that looks like this. But the cosine of 5t times 2 pi has a much longer wavelength. It looks like this. Now let's think about what happens when we multiply them. You see, when we multiply them, it's almost like the cosine becomes an envelope and the sine wave fits into that envelope. If you think about it, the sine wave is going back and forth between plus and minus 1. And when it gets to plus 1 and we multiply by the cosine, we're just getting the value of the cosine. And when it goes to minus 1 and we multiply by the cosine, we're just getting the negative of the value of the cosine. And that's why this function appears to be just wavering back and forth inside the cosine envelope. The cosine term is the one producing the beats. And that's telling us how fast the beats are. So let's look closer at that. On the right side, we have 2 times the sine of 445 times the cosine of 5. And it's the cosine of 5t times 2 pi that's giving us these beats. Let's listen to that in this particular case. And if we look at the waveform, and if we look closely at the scale, we see that in every second, there's 10 beats. It's 10 beats per second. Now, if we change the notes a little bit, let's take a 444 hertz and a 440 hertz tone, and let's hear what those sound like. And you could actually count it with your watch, or you could look at this waveform and look at 1 second of that. And what you can see is there are 4 beats per second in that. So once we've seen a couple of these examples, I think we're ready to make a conjecture. That's the mathematician's term for a good, solid, educated guess. When we had 450 and 440, we got 10 beats per second. When we were at 444 and 440, we got 4 beats per second. So the conjecture should be that if we have A and B, where A is a little bit bigger than B, we should get A minus B beats per second. Why? Because of the beat equation. But if we look at that beat equation, the right side has the cosine of A minus B divided by 2 times 2 pi. So you might ask yourself, why are we hearing A minus B beats per second? The frequency we just guessed was A minus B, but it looks from the formula like it should be A minus B over 2. So why the difference here? To understand this, we have to look back at that cosine. You see, the cosine has a frequency of A minus B over 2. That's true. And it goes down and back up, just like this. Every full wavelength of the cosine has to go down and back up. But when it does that, that single waveform, that single wavelength of the cosine produces 2 beats. And so the sound is beating twice during 1 full cycle of the cosine. And so that tells us that our conjecture was correct. It's not A minus B over 2 like the cosine would indicate. It's double that. And so we can our conjecture is correct, and we get a beat frequency of A minus B. Now let's also look at what happens when A is equal to B. Let's suppose that A and B are exactly the same and they're equal to some frequency f. Then on the right side of the equation, we have 2 times the sine of the average, well, the average of f and f is just f, times the cosine of half the difference. But the difference is 0. And if you remember from your trigonometry class, the cosine of 0 is just 1. Remember, the cosine is the x-coordinate on the unit circle, so that if the angle is 0, the point on the unit circle is 1 comma 0, and the x-coordinate is 1. And so the cosine of 0 is equal to 1. The cosine just disappears, and what we get is 2 times the sine of ft times 2 pi. It's just the original sine wave doubled. And in fact, if you look at the beat equation, that's what we get on the left side as well. We get the sine of f plus the sine of f. We just get 2 times that. Well, enough about this math theory and all of these theories of beats. It's not just a mathematical exercise. It turns out these beats are really useful. So let's see how they're used. Now we know from last lecture, lecture 5, that subtle changes in pitches have led to big changes in composition. In practice, how exactly do you make subtle changes in pitch? Well, the modern way to do it is to have an electronic tuner that tells you how you're making these small changes. But historically, we didn't have those tuners. How did they make these subtle changes? The answer is using beats. In order to see this, we have to go over to the piano and do a little bit of piano tuning. So in order to tune a piano, we need some tools here. Here's my tuning lever. And we also need some things called mutes. Let's see if we have some of these. Let's see. There's 2. I think I'm going to need 2 more. So here we have 4 mutes. And these are going to be used to dampen some of the vibrations that we're going to see. Now let's look at this. Let's look at an A. Here's the 440A. Let's look at a 220A. That's right here. Ooh, that sounds pretty bad. Now if you look really closely inside the piano here, there's actually 3 strings that we have on a lot of these notes. Down here there's 2 strings, and down here there's 1 string. But on this particular A, there's 3 strings. And I don't want to hear all 3 of them. I want to hear just 2 of them. So let's hear these 2. Now those 2 are definitely out of tune. And in fact, if you listen closely, you can hear that it's beating. Those beats are pretty fast, and what you do when you tune a piano is you put this lever on the end of the string and you slowly tighten or loosen it. If you remember back to lecture 1 we talked about how the tension on the string affects the frequency. And so if I adjust this lever, I'm pulling it a little bit tighter and letting go. I'm changing the tension, and that's changing exactly the frequency it's vibrating at. Now these two strings that we have here are a little bit out of tune. And as I adjust the lever, you can actually hear the beats. And just like on the violin, as the 2 frequencies get closer, the beats slow down. And when I finally get these 2 exactly in tune, the beats go completely away. So again, we have 3 strings here, and I'm only hearing the left 2 because I've muted the one on the right. And here's what it sounds like. And now I'll try to tune this from out of tune to in tune. If you listen closely, you can hear wah, 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 wah. Those are the beats. It still has beats. And when I finally get it in tune, then the 2 frequencies are equal. A equals B, and then all of a sudden our equation simplifies. We just get 2 copies of the sign. That's what we're looking for when we tune a piano. We're looking to get notes that exactly match up. These are called tuning a unison, when we have 2 strings that are supposed to be at exactly the same frequency, and that's what we're hearing. We're hearing tuning a unison, and we're using beats to do it. And as those notes get closer and closer, the beats slow down, and finally when they match up, the beats are gone. Let's see if we can hear this on a violin, because one of the surprising things is, so far we've heard that if you play 2 notes that are really close in frequency, your brain is hearing the right side of this equation. You hear these beats. And we've also heard that if A and B are far apart, your brain hears the left side. It hears 2 notes. But actually, you can hear beats when you play an octave out of tune. Let's hear these. I'm going to play an octave. Here's a G. and here's a G an octave above it. And if I play those, I'm going to play those a little bit out of tune. Listen closely and you'll hear the beats. And again, as I get them closer and closer to in tune, you can hear the beats slow down. And when I get them exactly in tune, it sounds almost like it's a single note, even though I'm playing octaves. Let's hear these beats on a piano. So on the piano, I'm going to play an A here at 440, and another A down here at 220. And in order to hear this really clearly, we want to hear just one of the strings of each of them. So on the 440A, I'm going to use these mutes to dampen the outside strings. And now when I play the A, we're only hearing the middle of these three strings. I'm going to do the same thing down here on this A. So now I've damped the outside ones, and we're only hearing the middle string here. I'm going to move my tuning lever so that I'm turning and tightening and loosening the middle string on the lower octave. And now let's play the octave. That sounds fairly good. If we pull this out of tune, let's hear what it sounds like. You can hear the beats. Wah, 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 wah. Let's hear it again. And now I'm going to slowly increase the frequency by increasing the tension on the lower one, and you're going to hear the beats slow down and finally disappear. And if I go too far, we get beats again. You can really hear the frequency of those well. Wah, 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 wah. Let me bring that back down to in tune. And when they're in tune, the beats disappear. So why are we hearing beats? Remember, we thought that when the frequencies were really close, we would hear beats. We would hear the right side of the equation. But when we were playing two notes that were further apart, we wouldn't hear beats. We're playing notes that are very far apart. In fact, they're octaves. They're about double. One frequency is double the other. So why is it that we're hearing beats? Somehow it seems like the beat equation doesn't really explain this. You see, if we played a note that was, say, at 442 hertz, and another note at 220. Now those are about an A, but the A is a little sharp. The 440 would be the correct one. So it's an A4, which is a little sharp, and the 220 is the correct A3. If we play those together, the beat equation tells us that we should hear the difference between them. We should hear 222 beats per second if we were hearing the right side of the equation. Now we're not hearing the right side of the equation, we're hearing the left side of the equation. We're hearing two notes. So why is it that we're hearing beats? We definitely did not count out 222 beats per second. We counted out something much slower than that. In order to understand this, we have to go back to the overtone series. You see, if you're playing one note at 220 hertz, you're hearing its overtones, all the multiples of 220, 440, 660, 880. If you're playing the higher note, 442, you're hearing its overtones, 884, 1326, all of the multiples of 442. The beats aren't coming from the fundamentals, which are 200-some hertz apart. The beats are coming from one of the harmonics of the lower A and the fundamental of the higher A. One of the harmonics of the lower A is at 440 hertz. The fundamental of the higher A is at 442. You're hearing both of those frequencies, and so you are actually hearing two frequencies that are very close together, and because of those frequencies, you're hearing beats. How frequent are those beats? Well, let's go back to the beat equation. If it's 440 and 442, you should hear 2 beats per second. And so if I had tuned the piano strings exactly to 220 and 442, you should hear 2 beats per second. Now this problem of beats when you play notes far apart, it doesn't just happen with octaves. It also happens with other intervals. The key observation is that if two of the overtones of two notes are close, we're going to hear beats. Let's look at a fifth. So a 440 hertz A, that's a correctly tuned A in the modern times. And a note at 293 hertz is pretty close to a D. Remember D here, the A is the fifth note on the D major scale, and that's why that's an interval of a fifth. Let's look at the overtones that we're going to hear, the harmonics and the overtones of these notes. If we play a 440, we're going to hear the fundamental at 440. We're going to hear the second harmonic, the first overtone, at 880, and then 1320, and then 1760. For the note that's really close to a D, the 293, we're going to hear its multiples as well. Its second harmonic, its first overtone, is going to be 586. The next one is going to be 879. The 879 is going to be very close to the 880 that we had as the first overtone of the 440A. So if we were to play these two notes, you would hear both of these overtones, these harmonics, and you would produce beats from that. We can ask a mathematical question here. What frequency should we put the D at in order to completely eliminate these beats? So let's see if we can solve that problem. Let's suppose we put that D, instead of at 293 hertz, let's put it just at X hertz. And now let's figure out what X should be in order to get a nice consonant sound and eliminate the beats. Now if we play something at X, we know its overtones are going to be multiples, 2X, 3X, 4X. And it's the 3X that we want to try to match up with the 880, the first overtone of the A. That gives us an equation to work with. It tells us that 3X should equal 880. That's an equation we could have solved a long time ago, probably in middle school. We divide both sides by 3, and we get that we should put X, we should put the frequency of this D at 279 1/3 hertz. Let's just check our work. We remember that a fifth, a perfect fifth, should have a ratio of 3 to 2. So if we take 440 hertz and divide by the lower frequency, which is 293 1/3, if we do that math, we do indeed get 3 halves. That is a perfect fifth. Let's see if we can hear these on a violin. Now, as we get to these other intervals, the effect becomes much more subtle. But it is a sort of a familiar sound. When you hear somebody tuning up, the violin gets an A from the oboe, or maybe the piano if it's just a violin piano piece, and gets the A and tunes that. And the next thing a violinist will do is tune the D. Remember, the A and the D, that's a fifth. So now I'm going to play my A and my D string. And one of the things a violinist is doing is listening for the dissonance between those until it's gone. Really, you're listening for the beats in there until they're gone. Now, most notes on a violin can be adjusted on the fly, so it's really no problem. If I'm playing this note, I can change it while I'm playing it, but these open strings, these have to be tuned fixed. And remember that tuning problems weren't just for pianos, and so violinists should actually tune their fifths to be slightly tighter, just like they were on a piano. Let's see what it's like tuning fifths on a piano. Good. We have the A set at a nice 440, and now we're going to look at tuning the D. Now here's the D. Again, the D has 3 strings, and so I'm going to take mutes to dampen the outside ones, and now the D should just be the middle string. And when I play those together, we get this. And now I'm going to tune the D, and I'm going to tune it up and down, and let's listen for the beats that we should be getting. You can definitely hear the dissonance in this. You might be able to hear the beats. Let's see if we can hear these a little clearer. When I'm doing this exercise with students, one of the things I have them do is I have them come over and touch the piano. When I play this, you can actually feel the beats a little bit better than you can hear them. Now what we just calculated is that if we want a Pythagorean or a just-tuned tuning system, if we want this fifth to be perfect, we should aim the D for 293 1/3 hertz. And that means aiming it for perfect fifths so that there are no beats at all. Let's listen, see if we can do that. You can hear I went too far. Let's bring it back down a little bit. That sounds pretty good. Now that was a Pythagorean or a just tune system, but this is a modern piano. We don't want the fifths to be perfectly in tune. Remember, we needed the fifths to be slightly narrower. We needed the ratio to not be 3/2, but this irrational number that we came up with, 2 to the 7/12. So how should we tune this? Well, what we're going to do is we're going to use math to figure out the frequency for the D, what it should be. And then we're going to use that and the beat equation to figure out how fast the beats should be when we play that D with a 440A. And then we're going to use that to tune the D. So let's do that. So the first step is to find the frequency for a correctly tuned equal tempered D. That means adjusting the fifths so that the octaves will work out when we get to the top, spreading that Pythagorean comma completely evenly around all of the fifths. Remember, the half steps were tuned to 2 to the 1/12, and the fifths, that's 7 half steps, were tuned to a ratio of 2 to the 7/12. So if the A is tuned to 440, then the D should be tuned to some number Z, some frequency Z, so that Z times 2 to the 7/12 is exactly 440. We can solve that equation. We divide both sides by 2 to the 7/12, and then we can use a calculator. And what you get is that the D should be tuned approximately to 293.66 hertz. So the next step is for us to figure out how fast the beats will be if we tune it exactly that. So if we play the 440A, we'll hear all of its overtones, including the pure 880. If we play a note, the D, the equal tempered D at 293.66 hertz, then we know its overtones are just going to be multiples of it. And the second overtone, the third harmonic, is going to be at approximately 880.99 hertz. Now we can use the beat equation to tell us how frequently the beats should beat. Remember, the beat equation told us that the difference between those was going to give the frequency of the beats. And so the difference between 880.99 and the 880 first overtone of the A is going to be about 0.99, just a hair under 1 beat per second. So all of this is telling us if we want equal tempered fifths, we should tune the fifths so that they're not perfect, but they're narrow, just enough so that we hear 1 beat per second. So let's go here on the piano and see if we can tune the D in this equal tempered way. So here's the A at 440 hertz. And here's the D that we tuned perfectly at 293 1/3 hertz. And now in order to tune this piano, this particular interval in an equal tempered way, we're going to have to make the D a little bit sharp. How much sharp? Enough so that we hear just about 1 beat per second. Let's listen. Can you hear those beats? Wah, 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 wah. That's definitely faster than 1 beat per second. That sounds about like 1 beat per second. One of the things that piano tuners do, a really classically trained, probably an older piano tuner, they could tune a piano with just an old school watch, and they could just watch the seconds beat, and they would count beats like that. But essentially, you now know everything you need to know in order to tune a piano. You tune the fifths in this way. Now you have to be careful. It's not that every fifth has just 1 beat per second. You actually have to go back and do the calculations and figure out how many beats for each one of the fifths, because it changes as you go from the bottom to the top. Again, because it's multiplicative. But you do this process. You can tune the fifths by calculating them, figuring out how many beats, and tuning them exactly like that. And then you tune the octaves perfectly. It's a little bit more complicated because you have these multiple strings. And once you've tuned one string, you have to remove the mutes and make sure the other strings on that particular key are tuned exactly the same. You have to tune what's called the unisons again. Now, I have to give you some disclaimers about this. This isn't exactly how piano tuners do this. Among other things, they don't go on the side and figure out the math every time and then come back and tune a fifth. Many of them use electronic tuners, and in fact, some of them don't tune in an equal-tempered manner. Some performers don't want their pianos tuned in an equal-tempered way if they're playing a particular piece. Piano tuners also have these really interesting rules of thumb. For instance, the one that I find really funny is if they're listening for something that's 7 beats per second, instead of using a watch and counting out wah, 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 counting out 7 per second, some of them will use the phrase "from Chicago to New York." And if you say the phrase "from Chicago to New York" in a single sentence, in a single second, then that's telling you how fast the beat should be, because "from Chicago to New York" has 7 syllables in it. A lot of piano tuners, instead of tuning the fifths, will actually have a very specific sequence of intervals to check. And it's not just fifths. A lot of times they'll tune something and they'll tune it with another interval and they'll be checking to see to make sure that one beats slightly faster than the other or one beats slightly slower. That's another thing that piano tuners will do. Instead of actually counting the beats per second, they'll just compare them with other ones that they've already tuned so that they would know that one interval should have beats just a little bit faster or just a little bit slower than another interval. Also, I want to admit that the mathematics we've talked about here is a little bit off, and it's off for a very interesting reason. See, the widths of these strings inside the piano are actually coiled, and that changes things. The coiling of the strings actually takes the overtones slightly sharp. If you remember back to the mathematical models we were talking about in Lecture 1, when we talked about those models, we assumed that the strings were infinitely thin. And only under those conditions were the overtones exactly at multiples. When you take into effect that these strings are coiled, then, for instance, if you play a 400 hertz fundamental note, the first harmonic is the second harmonic, the first overtone, is not at 800 hertz. It's a little bit higher than 800 hertz. And piano tuners have to take into account this effect, and they do it in a really subtle way. You see, because the overtones are a little bit high, piano tuners have to do the following. And you can sort of think about it on the piano here. You see, in the middle of the piano here, they're tuning things just fine, but then say the overtone of this note is going to be a little bit too high, higher than the math would first predict. And so when they get to these higher notes, they have to take those frequencies up a little bit. And this is called the stretching. And when you go back down the other way, you want to make sure that the frequencies that you hear when you play a lower note exactly match up here. But the overtones of the lower note are stretched. They're a little bit too high, and so you bring the frequencies on the left side a little bit down. Tuning this gives you what's called the stretch of a piano. And this tells you that really piano tuning is really an incredible art. It's not so much of a science, although science certainly goes into it. The really great piano tuners are tuning by ear, not by electronic tuner. And it's not just about tuning. It actually matters when you play the music. And so let's go and let's listen to some music and talk about the implications of all of these beats and this tuning on music. So remember that the overtones included things like the octave, the fifth, the fourth. Musicians call these perfect intervals. When you play these intervals, it requires greater precision. If you play them a little bit out of tune, you're going to hear beats. Think back to the opening music when I was playing the slower part of the chaconne. Some of the intervals, the tuning wasn't as crucial. It was the octaves. I played an octave, and it was very crucial that I get those exactly in tune. The same is true of the other open intervals, the fourths and the fifths. And this happens on almost all instruments. You want to make sure that your octaves, your fourths, and your fifths are exactly in tune, because if they're not quite in tune, you're going to hear beats because the overtones of those should exactly match up, and if they don't, you're going to hear beats. This becomes really important in some music. So let's hear an example on brass instruments. Aaron Copland was an American composer. He lived from 1900 to 1990. He was born in Brooklyn. His parents were Lithuanian Polish Jews. And he wrote a lot of music evoking the American spirit, the wide open Western landscape. And one of the ways he got that sort of open feeling was by using open chords, these octaves, the fourths, the fifths, the perfect intervals that we were just talking about. A great example of this comes from 1942. He wrote a piece called The Fanfare for the Common Man. He wrote it for the Cincinnati Symphony, and it premiered in March of 1943. It was inspired by Vice President Henry Wallace's speech, Century for the Common Man. And when you listen to this, you're going to hear many perfect intervals. You're going to hear a lot of these fourths, fifths, octaves, these open chords. And we hope that the musicians who are playing this practiced for hours to get those exactly in tune, because if they're not exactly in tune, you're going to hear dissonance, you're going to hear beats. And one of the things they're practicing to do is to avoid that dissonance. Let's listen to the Copland. That almost makes me want to go over and join in and play the timpani part. So let's see what we've learned to this point in this talk. When you play two frequencies that are very close but not equal, you hear dissonance, you hear these beats. These are predicted by mathematics, it's trigonometry. And we can use this phenomenon in piano tuning, and we try to avoid this phenomenon in performance. Now usually we're ending these talks with a musical coda. Today we're going to end this with a mathematical coda. Now, virtually everything we've done today relies on this single equation, the beat equation. In most lectures that we're talking about, the mathematics would take far too long to derive. Think about the Fourier transform. It would take semesters. Today is the exception. All you need to understand this trigonometry is, this trigonometric formula, is some of the trigonometry you probably saw in high school. Now, if you were turned off by the abstractness of trigonometry back then, and you weren't alone, now's your chance to really appreciate the meaning of trig in the context of music. So let's take these last few minutes and prove the beat equation. So here's the beat equation, and the things we need to remember in order to prove this are that the sine is equal to the opposite over the hypotenuse of a right triangle. And if you happen to be on a circle of radius 1 called the unit circle, then the hypotenuse is 1. And then the sine is just the opposite, the length of the opposite, the y value. And the cosine is just the length of the adjacent, the x value. We also have to remember that cosine is an even function. That tells us that cosine of negative x is equal to cosine of x. And sine is an odd function. That tells us that the sine of negative x is equal to negative sine of x. The last thing we have to remember is that the sum of the angles in a triangle is 180 degrees. So let's see if we can do the proof of this beat formula. Before we get to the actual proof, let's simplify the formula we're trying to prove with a little bit of algebra. You see, on the right side, we have the average of A and B, and we also have half the difference. Let's change variables to simplify that. Let's let U equal A plus B over 2, the average, and let V be A minus B over 2, half the difference. When we do this, then when we add U and V, the B over 2's cancel, and we just get A. And when we subtract, when we take U minus V, the A over 2's cancel, and we just get B. And when we plug those into our formula, the beat formula is equivalent to, in U and V, the sine of U plus V plus the sine of U minus V equals 2 times the sine of U times the cosine of V. We're actually first going to prove a formula for this left side. We're going to prove what's called the sine of the sum formula. The sine of U plus V is equal to sine of U cosine V plus cosine U sine V. After we prove it, we're going to use it twice. Let's just use it now, and we'll come back and prove it later. We use it twice on the left side. We have the sine of U plus V. We can use this formula and write out what it equals. We have the sine of U minus V. We can use the formula and see what it equals. And now we can use the even and odd formulas for cosine and sine to simplify the right side. When we do that, we see that these two terms cancel. The other two terms are identical and just add. And so we see that we just get 2 times the sine of U times the cosine of V. And that's what we were trying to get. Now let's see if we can prove the sine of the sum formula. That's the last thing. If we prove that, we've proven the beat equation. To do that, we need an angle u and an angle v. So let's put the angle u on the bottom and put the angle v on top of that. And let's measure out 1 unit on the top ray. Let's call that point B. Now the sine of u plus v should be the y-coordinate of b because the hypotenuse is 1 here. So we're really looking now to figure out how far is b away from the x-axis. That's the y-coordinate of b. In order to see this, we need to draw a few lines. Let's draw the perpendicular to the middle ray from b, and we'll call that C. And now at C, we'll draw a vertical line through C, and we'll also look at B and draw a horizontal line through B. That vertical and horizontal line, they intersect, let's call that E, and the vertical line hits the axis, let's call that D. And now let's examine this picture. Remember that what we're looking for is the y value of B, the distance from B to the axis. And that is just the length of ED. You can see that ED is split into two pieces. The bottom part is DC, and the top part is CE. In order to figure those lengths, let's first look at the right triangle ABC. Now the right angle here is at C, and the hypotenuse is AB. That's just 1. And therefore, AC has length cosine of V, it's the adjacent, and BC has length sine of V. Now, let's look at triangle ADC. The angle there is U, and the sine of U is going to be the length CD, the opposite, over the hypotenuse AC. We figured out that AC was the cosine of V, and now we can multiply both sides by cosine of V, and we've solved for CD. It's sine of U cosine V. We're halfway there. We got the bottom part of the line segment, and now we have to get the top part, EC. To get EC, first we want to figure out what angle is at BCE. To see that, there are 3 angles meeting right here at C. One of them is 90 degrees, which tells you the other 2 must add to 90. We call those complementary angles. Now we know another pair of complementary angles. It's these 2. With a right angle at D, all 3 of these angles have to add to 180, but the right angle is at D, and so these 2 angles also have to add to 90. Well, if this pair adds to 90 and this pair also adds to 90, these 2 must be the same. And that tells you that the angle right here at BCE is actually equal to U. Let's use that to get CE. Now we know the length of BC, that's sine of V, and we know the angle right here. So let's look at that triangle. The cosine of U should be the adjacent, EC, over BC. That's EC over the sine of V, and when we multiply both sides by sine of V, we get EC. We get EC as the cosine of U times the sine of V. And that really completes it. You see, the sine of U plus V should be the y-coordinate of B. That's the length ED. That's split into 2 pieces. And now we've solved for the lengths of both of those. With just a few trigonometric facts and some basic geometry, we finished the beat formula. We proved it. Now, even if you didn't follow the proof, you can see what it shows. It implies that when 2 notes are just slightly out of tune, we should get this discordant sound. We should get dissonance. We should get beats. It tells us why musicians have to be more careful with some of the intervals than others, like the slow part of the chaconne that I played at the beginning. It shows us how piano tuners use this dissonance, finding ways to tune pianos in an equal tempered system that solved the piano tuning problem. Now next time, we're going to look at probably the most obvious connection between math and music, rhythm. Thanks for joining us.